we observed that curl equations, when what you have this curl of E and curl of H. So this curl equations predict propagation, or simply you have wave propagation otherwise. Okay, and we observed and just confirm whether or not we did this. Del square E plus K square E equal to 0. Did we complete this?
No, sir.
Hmm?
No, sir.
No, sir.
Are you sure? Because I think I...
No, sir. We did not complete that.
Okay, but...
Sir, you have explained about spatial frequency and
Yes, sir.
response and the cause.
But are you seeing this document? I just explained this one to you, right? Did I explain these things?
Sir,
Le-
this is for A3, sir.
Oh, did I explain this one? This particular one. Are you seeing this? No?
No, sir.
No, sir.
Okay. I've done this for A3 then, okay. So anyways, del square E plus K square E is equal to 0. 1 second. What I have here. Mm, okay, I did not explain this to you. Okay, it will take time then. Anyways, not a problem. This is a very, very important lecture. Everyone, please to follow properly. If you have any doubts, just raise. Because this, now whatever I'm going to do, this is not in your textbooks. Your textbooks did not mention these things, but these are really important things for height studies and gate point of view as well. So what we have already is, so we proved that when electric field is polarized in x-axis and propagating along z and varying in time as well, so you have represented like this: ax naught cos omega t minus k naught z plus phi 1 plus backward wave ex naught cos omega t plus k naught g plus phi 2. Did we complete this one?
Yes, sir.
Yeah, this is done. Now, okay, the same thing we can also arrive differently. That is, the curl equations, as we know very well, you have curl equations. Curl of E is minus dou B by dou T, and also we have curl of H is equal to dou D by dou T. So we assumed source-free medium, right? So we assumed source-free medium, and then we constructed Maxwell's equations like this. There is no JC here. Conduction current density is missing because in a source-free medium, I want to show propagating waves in the source-free medium. That means in this medium, there are no further charges or there are no sources of any current or something like that in this medium. So you have, so this medium is devoid of, say, this medium is devoid of all these sources or something like, I mean, devoid means there's nothing. So you have an empty free space, something like this. So in this case, you have a propagation. That's what we want to understand now. Okay. So for that, we know that very well. You have these things and these equations. Uh, these I just don't save it. Okay. So just so these equations. I mean, so in free space, I have curl of E is equal to minus mu naught. So you have dou H dou T and curl of H is equal to epsilon dou E by dou T. I was just explaining this to section C. How come this, these curly equations, they predict propagation or they predict wave phenomena or wave propagation. How come that is true? That so that we will check with this. For example, you see, let's take see because that means at a point, you take some point in free space. At that point, magnetic field is varying in time. If magnetic field is varying in time at a point in free space, and that will induce spatial variation of electric field. Not only electric field varies spatially, but also electric field varies temporally or in time domain. I mean, or in time. Sorry. So what I meant to say is this: I have a medium at which I have a point. At this point, we would see, say, magnetic field is just varying like this, up and down. Okay, say magnetic field is oscillating like this at a point. I just took only one vector to show the magnetic field, variation in time. I'm just showing it like this. Okay, now what happens is that when magnetic field is varying in time at a point in free space, now around this point you would see electric field induction. That means electric field will be produced now like this all around the point. All around the point you have electric field like this. Yeah, because you have curl of E. Curl of E is not equal to 0 because you have something on the right hand side. So you have curl of E now. Okay, so now you tell me this guy is H. I have negative sign, that is for Lenz's law of the account now. That means you put your right thumb along this. See, at this frame, I mean, at this point of time, see, within this frame, say you have magnetic field is upwards. Okay. Now take your right hand thumb. Now the curl is along these white dots. Okay. That I mean the fingers, four fingers, they're along these white dots like this. Now what I do, as I have negative sign, so can I put like this electric field? So now my electric field is something like this. Agree? Agree or not?
Yes, sir.
Yes,
Yeah,
sir.
this is my electric field now. So now electric field is having curl all around the time varying magnetic field at this point. Okay. Now, not only this, now you have this curl of E, that's true. So this negative sign indicates that the induction will be just opposite now. So now, after a certain point of time, delta t point of time, this magnetic field is coming down now. Now, in this case, what happens? Electric field will go anti-clockwise. Okay, so clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise, anti-clockwise. The moment this H is going up and down, electric field will go clockwise and anti-clockwise. Yes or not? So they vary in space as well as in time, because when H is varying in time, electric field is also varying in space as well as in time. Agree?
Yes,
Agree.
sir.
Yeah. Now you just take electric field. This is, let me take it. Let me take any one electric field vector. Okay. Any one arrow like this. Now, when electric field is varying in time at a point, let me take, this is my point. Let me, this is my point. Now, electric field is C. Now what happened is that when H is going up, electric field is like this. When H is coming down, electric field will go this anti-clockwise. That means electric field will also behave like this. Okay. Electric field is also now varying in time at a point like this. Now it is the case. Now around this point, I would take something like this. Okay, so around this point where electric field is varying, see, it is coming towards you and into the boat, towards you and into the boat. Okay, now that will produce magnetic field curl. That means you have, there is no negative sign here, so you put your right hand thumb along this E towards you. So therefore, how is the magnetic field now? How is the magnetic field now? Is it right? Is it okay? You put your right hand thumb along this arrow, okay, and you curl your fingers along these blue dots. Now, how do you get the magnetic field? Agree?
Yes, sir. Yes, sir.
Yeah. So this must be. So this is what your magnetic field now. So now, see, when electric field is going into the board, magnetic field, it will show a clockwise direction. I mean, it varies spatially in clockwise. When it is coming out of the board, it varies spatially anti-clockwise. So anti-clockwise, clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise. When this E is keep on oscillate, like at this point. So now, again, what happens? Now I just take this magnetic field. I have this magnetic field, H. I take this point now. Okay. Now see, magnetic field is say is going like this. Say upwards in this case. Now it can also come downwards after that relative point of time. So H is say varying up and down again this way. H is varying again up and down. So perpendicular to this, in the perpendicular plane, you have this again curl of E. If H is something like this, perpendicular plane, you have this E. This is H, this must be E. Okay. So now again same story like this. At a point H is varying in time. Okay. Now all around this H, you have this electric field. Now in this frame, H is showing upwards. When H is showing upwards on this frame, I can take my electric field like this. Okay, again it will go down, electric field will be now anti-clockwise. So anti-clockwise, see, that means clockwise, anti-clockwise, clockwise, anti-clockwise, when it is varying in time. Now again you take electric field like this. Okay, electric field like this. Again at a point, if electric field is varying in time, it will produce curl of H all around. Are you getting this?
Yes, sir.
Yeah, so like that it keep on moves. That means, see, because of time variation of H, see, that means electric field is not only here, you have also electric field like this all around. You have fields. I took randomly any one electric field like this, some electric field you have like this. So you have magnetic fields this way, electric fields all the way like this. Yeah, so on. Now see, the journey you initiated here and you kept propagating all the way like this. See, you're going this way, yes or not? That is that's the beauty of these curl equations. I started up here, I'm reaching all the way here, and again I took some point here, some variation over here that induces a magnetic field here, and this magnetic field is, see, magnetic field is all around, not only this outer ring. Magnetic field is also here, is also here. Okay, I'm just taking any one point in its vicinity, so I'm just going this way. So now I'm propagating, right? I'm propagating from one point to other point like this, right? So Maxwell predicted this. Maxwell predicted wave propagation this way. Yeah, propagation is happening this way. Are we clear so far? Because this is, everyone says that time varying magnetic field will produce electric field. Time varying electric field will produce magnetic field. But I know out of say 10,000, out of 10,000 students, one or two will give this picture clarity. I can bet this. I asked many students this one, how do you come to know that time varying H will produce E, time varying E produce H, and this leads to propagation. I just asked many to draw this picture, but hardly I found anyone did this. Perfect. So are we clear so far? I just want to put this in front. So are we all clear with this?
Yes, sir. Yes, sir.
Everyone, please raise your hands if you understand this. Raise your hands if you understand this. Why only three? It's better to remove remaining from the meeting then. If people didn't understand, there is no purpose, because I'm giving 10 more seconds to you. Okay, you just tell me properly. If you didn't understand, raise your voice, saying that I didn't understand. If you understand, just raise your hands. Okay, now count starts. You know very well. If I say means I'll do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. How many of you there? So, okay. So I'm seeing Subhadeep didn't understand. Srikar, Deepak, Ayush Mahajan, Jagadish, Ravi Vikas, Salma Sultana, and Gogineni Pujita, Sushant Reddy, K. Veera Mohan Reddy, Raghavendra Sai, Srihari. Then what the hell are you doing? Should we remove you? Please speak out.
No, sir.
Then why don't you tell me something? I just told you a moment ago. If you didn't understand, just raise your voice and ask me. If you understand, just raise your hands that you understood things. So, but most of the students didn't. So, remaining, Subhadeep. So you didn't say anything. So I just want to remove you now. Subhadeep, are you there?
Yes, sir.
Why didn't you answer, man? Did you understand or not?
No, sir.
No, no or yes?
No, sir.
Then why didn't you ask me no? I just told you if you didn't understand, just raise your voice and ask me. Then why didn't you ask me? That's a very important, aspect of Maxwell's equations. I just try to explain that. Why didn't you ask me then? And whoever raised hands, are you really clear with that idea? Did you really experience that?
Yes, sir.
Yes, sir.
Why remaining just dumb like
Yes,
that?
sir.
I think every one of you knows English. I think you can understand English. Yeah. Ravi Vikas Konatala. Ravi Vikas. He isn't there. Ram Jagadish. Gogineni Pujita. Sushant Reddy.
Sir,
Did you understand?
sir,
Did you understand to what I explained a moment ago?
yes, sir.
Then why didn't you raise your hand? I just asked you students, if you understand things, just raise your hand. If not, just do ask me.
Sir, I raised my hand, sir.
Why now? Why this tardy response? I mean, why the late response? Are you here in front of your system or elsewhere?
Yes, sir, I am here only, sir.
No, then why didn't you raise your hand? Please respond to things immediately,
Okay, sir.
because that bothers me a lot, because I don't know whether people are turning up from their end or not. How can it?
Yes.
Because this is not physical classroom. So
Yes,
please, you
sir.
have to cooperate. And
Yes,
we
sir.
are
Surely, sir.
okay, fine. So we are almost we're going to culminate things very soon. So see, if you didn't understand, you have right to ask me. Please do ask me things. That's it. Yeah. If not, then just respond. Okay. You have to respond somehow. Otherwise, how would I come to know that whether you're getting things or not? Physical class means definitely you will come to know what is what and who is who and how to respond or whatever it is. See, virtual class, I really don't want to waste my time in discussing all other things except this. First of all, we don't have time to discuss our subject and what else we discuss. So until and unless you cooperate, we cannot move further. Okay, anyways, fine. Not a problem. So we understood these Carly equations predict propagation. 39 participants raised hand. Okay. So out of 39, I don't know how many of you are sure about your understandings. So anyways, fine, great. That's good. Okay, fine. See, anyways, here I'm here. I just really gave a very simple paper for end exam. Yeah, just to help you out in getting, in making good score out of that. So just tell me if you want any difficult paper. Definitely will make a difficult paper for you.
Sir, somewhat you can raise your voice, sir. That's only my problem.
Okay, the problem is that here, along with me,
Hearing, sir.
yeah, along with me, other two faculties are also taking class. So that's the problem. So we all in same cabin. I'm sorry for that. We all are in same cabin, so I cannot raise my voice.
Some words yeah, I'm unable to hear, sir.
Yeah, then do one thing. If that is the case, do you have any MI speaker or board speaker?
No, sir.
Do you have earphones?
Yes, sir. Yes, sir. I'm
Then
having.
you please use it. Raise the volume, raise system's volume. Nothing will happen for 1 hour. Just use
Okay,
it.
sir.
I'm sorry because
Okay, sir.
thing is that simultaneously other classes are also active. So we should not disturb. I mean disturb them, right? So please,
Yes, sir.
yeah. So please cooperate in this regard. So I'm sorry. From tomorrow onwards, I'll try to go to other room, and we'll do that. Don't worry.
Okay, sir.
Okay.
Thank you, sir.
So we know that since the curl equations predict propagation, now it makes sense that. So it makes sense that we derive wave equation. So now we derive wave equation by combining the curl equations. So first of all, you have to understand the motivation behind any derivation. Okay, because why are we going to combine those wave equations? Why? See, why are we going to combine the curl equations? Because couple of moments ago, we observed that these curl equations, they predict what? Propagation, right? Right or wrong?
Yes, sir.
Yes, sir.
Yeah. As they predict propagation, now we are really eager. We are thrust. We are thrust to find this wave equation out of this propagation. So to investigate, to explore this fellow, so now we are in a process of combining these two curl equations. Yeah, because as of now, what you have is that this E and H, they are coupled. Okay, H and G, because I want to decouple E and H, and I want to show equations only in the form of E and again only in the form of H. Now, when you have both E and H involved in one equation, I can't really segregate. If I'm able to segregate E and H from these equations, now how do I know electric field is going something this way one dimensionally? And how do I know magnetic field is going this way, one dimensionally? I just want to make only E field is going all the way and only H is going all the way. Yeah, then we can combine these two anyhow in the, at points of interest, and we will say propagating is something this way. So first of all, we have to show an E wave, all right? So for that, see, let me show plane wave, chief, plane wave chief. All right.
If you want to plot just one cycle of message signal means obviously A and cos 2 pi from case nothing. That's only one cycle of message signal you want to plot. Or simple.
Let me take one good wave. Okay, this is somewhat good, I think. This is not pretty good. Let me take this.
One by 100 means 34, 0.01. 0.01 is greater than 0.005 or less than. If it is greater than, then if this time limit, how it can plot one period of.
I think this is good.
Minimum required is 0.01.
This is too small to go. Nothing is helping us.
So it is not possible. You can see only half. Yes, no. That's why the red color plot come only half. Not one period.
Are you seeing this?
Yes, sir.
What are you seeing now? You can down your hands, okay? So what are you seeing now? You're seeing red wave and blue wave, okay? The red wave is electric field and the blue wave is magnetic field. Are you able to see this animation?
Yes, sir.
Yeah. Now we want to show only the red wave and again that magnetic wave individually. Okay. If I want to show them individually, because see, as of now, the spatial variable is what in this case? A spatial variable in this case, of course, it is showing
Yes,
X
sir.
here. In this case, it is showing. Oh, let me make it big. The spatial wave, that means, okay, in this example, he took the wave is propagating along x-axis. That means the electric field is only varying spatially along x-axis. So we did not take anything along y and z. But in general, in free space, the wave won't propagate like this. Yeah, because free space is all 3 dimensions. So in 3 dimensions, we have to cover the wave propagation. But for simplicity, as of now, we took only one-dimensional propagation. Okay, so we will slowly replace that one-dimensional by 3-dimensional, and that's what your plane waves. So that we will see. Okay, those plane waves. So I just want to show them how E and H separate equations. So therefore, I want to decouple. I want to show equations only in the form of E and H, so that I can show complete E wave and H wave individually. Okay, mm, for that now what we do is this. I'll not save this. So I can take my, you will come to know. So again, let me rewrite these equations. Curl of E is equal to what do we have? Minus mu naught dou H by dou T. And again, curl of H is equal to what you have?
Epsilon naught into dou E by dt.
Epsilon dou E by dou T. So I write this in phasor form, and I will tell you a little bit later what this phasor form is. Okay, so now this is nothing but curl of E is wherever you have dou by dou T, replace that by j omega. So okay, So I take minus j omega mu naught h. So wherever you have dou by dou t, you just take, and this is of course, we can say this is in frequency domain otherwise. So I'll just tell you how did we do this. It's a very simple, there's no big deal in this. You can even you can find this out. So j omega epsilon e. So wherever you have this dou by dou t, replace that by j omega. Okay. So I
Sir,
have this. Yes.
sir, one doubt, sir.
Yes, please ask me.
Sir, it's like in Laplace, if we take a differentiation in time domain, it will be multiplied with s, like that only we are taking here, sir.
Yeah, obviously.
So is it
See,
Fourier or
see.
Laplace
For
we are
example,
taking?
you see, there is no Laplace here, please. Yeah.
Fourier.
Yeah. See, you have learned Fourier series. Yes or not?
Yes, sir.
Yes, sir.
Did you learn Fourier transformation?
Yes, sir.
Yes, sir.
Yes, sir.
You have continuous time Fourier transformation. You have discrete time Fourier transformation. You have discrete Fourier transformation. You have fast Fourier transformation. You have Hadamard transformation. You have wavelet transformation. You have discrete cosine transformation. You have discrete sine transformation, so on. So putting things together, you can segregate the departments into two pieces. That means in the first piece, you have, say, Fourier transformation. So when I say Fourier transformation, I have continuous time, discrete, fast Fourier, okay? You put these things in one department. In the other department, you have Laplace transform and jet transform. Then why do we do all these things? You have a system, okay? You have a system. To analyze this system, for the analysis point of view, I require Fourier techniques. And for the design point of view, I require Laplace and jet transforms. That's it. End of the day, before I design a system, I must analyze it, every nuance of that, its behavior. So this guy is really helping us. That's what, before you learn any transformation technique, you have to understand the reality, the reliability, okay, the feasibility, and for what purpose you're doing that. One thing is true, you can design a system only if the output is known for a given input. Yes or not?
Yes, sir.
Yeah, if I know this output for a given, if I know this output for a given input, then based on this estimation, I can design this. Okay. So therefore, to do all the stuff, I require this Fourier techniques. And end of the day, I have to design a system. I have to make it reality. So if you want to make it reality in continuous time case, then I go with Laplace transform. If you want to make this reality on discrete domain, go with jet transform. Yeah. So whatever is impossible in discrete time Fourier transformation, that is possible with jet transform. So anyways, so I'm not dealing with these things for your semester. So it's a very interesting part, but without knowing these things, if you learn Fourier series, Fourier transform, all the stuff, what is the use? There is no use, please. So you should really wonder why the hell we need to learn all these many transformation techniques and all these things. Slowly you will come to know what I want to say every time is, without knowing the purpose, learning something is of no use. That's it. Okay. So this guy Laplace transform is pretty good for low frequencies, but when you go to high frequencies, this guy is absolutely a failure. Yeah. So you need to say bye-bye to Laplace transform, because you know the discrete time counterpart of Laplace transform is jet transform. All right. That means you say if x of t Laplace transform is like x of s, and you would say x of n jet transform is xg. Jet transform అయిపోయిందా?
No, sir. Maxwell అయిపోయింది, sir.
Yeah, Maxwell అయిపోయిందా? So jet transformation alone will not suffice the purpose. Jet transformation will have its life only after considering reason of convergence. So anyways, we'll not go to those things, because the uniqueness of the time domain function is decided not only by this compact form. This guy plus this guy will decide the uniqueness of signal. Okay, so those things you will learn anyways, don't worry. So this is all in discrete domain, you do the stuff. Okay, as you are using computers for the analysis purpose, so you have to say bye bye to this, time domain things, I mean this continuous things, sorry, and you have to invite this discrete stuff. So discrete time to discrete Fourier, discrete Fourier to fast Fourier, and so on. So Laplace electrical people require these transforms, jet transform. Of course, electrical people also require these things, but the thing is that you have to understand for the analysis purpose you require, for the design purpose you require this. Okay. Anyways, let's not deviate and let's not belabor these points. Let's motivate our discussions. Okay. The main aim of signal processing is not to extract information, not only to extract information from a signal. That's a basic answer. The right answer would be, you are in a set of right computational tool to process information, and in doing so, you keep moving from Fourier series to CTFT, CTFT to DTFT, DTFT to DFT, DFT to FFT, wavelet, so on and so forth, like that, to find a right mathematical tool. Anyways, so I have curl of E is equal to, and you will come to know how this j omega and all a little later, don't worry. And curl of H is equal to j omega epsilon E. Now I want to combine these two curl equations to find solutions for E and H. Okay, so now what I do is, let me do one thing. I just take mu here. You just try to understand. I just take mu H. I'll not take any mu naught in this case. And I take a curl of 1 second, please. Sorry. Here, sorry, did I do any mistake? Hmm? Yeah, I'm talking to you, dear ECE section A. Did I do any mistake in my equations? Are you there? Wow, tell me, are you there or not?
Sir,
It's gone.
Yes, sir.
in place of H, you
Can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Can you hear me?
Yes, sir, we can hear
Yes,
you.
sir.
Sir, we
Yes,
can
sir.
hear you, sir.
Oh my God, I'm sorry. Can you hear me?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
I'm
sir.
sorry. I'm very sorry. One of my, one on. Okay, sir. One end of my earphones is elsewhere. I'm sorry. I think you keep saying something I could not hear. Now, okay. So curl of H is equal to j omega epsilon E. All right. So now we will bracket this guy. So mu and epsilon. Okay. See, if I go to a three-dimensional space, this epsilon is not epsilon. Epsilon is a 3 by 3 matrix. Yeah, so I have like epsilon 1 1, I say epsilon 1 2, epsilon 1 3, epsilon 2 1, so on, epsilon 3 3. So you have a three-dimensional stuff. I mean, you have 9 elements for epsilon if you go in 3 dimensions. But really, we're not accounting all these things because this is true in inhomogeneous medium. The quite interesting fact or intriguing fact about this EM waves are that EM waves are transverse waves. They are transverse by nature. So they are not longitudinal like acoustics or sound waves. Okay, that means transverse waves. As EM wave is a transverse wave, and of course EM wave it doesn't require any medium for its transmission. So medium is there or not, doesn't matter. EM waves can travel. So medium isn't there indicates what? Say vacuum, there is no medium. So in this vacuum, no sound can travel, but EM waves can travel, light can travel. Okay. For example, in the medium, you take water. For example, you take a pure water, some water like that. EM waves can travel in that. Of course, sound also can travel. You take any other medium, you take any other dielectric medium, EM waves can travel in that. Now we take a medium and this medium is devoid of any particles in that. So this medium is absolutely free from all the particles. Nothing is in that. So vacuum EM waves can travel happily. And EM waves love to travel really. So you could say, let me take red. So EM waves it loves to travel in this vacuum. Okay. You love to travel in the vacuum. So this guy is vacuum. And this is also dielectric medium, but this is pure dielectric and this is dielectric medium. EM waves, okay, they just go, they're just happy. But here they love, yeah. So it loves like anything. So EM wave love this. Now we are trying to show this E and H as waves, one-dimensional waves. One-dimensional waves in free space or vacuum. When I say free space, it's absolutely ideal. A vacuum I take. So now in this medium, so this free space, what we consider this free space as linear, homogeneous, and isotropic medium. So we are going to discuss, we are going to derive the wave equations by considering our free space or vacuum to satisfy these conditions, linearity. So I have, let me use another ink. So my medium is linear and homogeneous and isotropic. Okay, now this is really so that I can form a reliable wave equations, trustable wave equations otherwise. Okay, because mathematics is convenient to develop some equations satisfying these three properties to your medium or a media. When I say media, you have plural form of medium. Okay, so now what is this linear medium? For example, you see, let me talk in terms of, for example, you have a medium, and in this medium, say electric field is something like this. If electric field is something like this, now In the same direction also you have D. This guy is say D, this guy is say E. Or in simple words, for example, you have D is equal to epsilon E. You know this very well. Okay. Now, to maintain linearity between these two quantities D and E, who must be constant now?
Epsilon, sir.
Epsilon, sir.
Epsilon must be constant. But you know what happens? Based on the applied electric field in general, in a practical medium, epsilon of that medium will change. Yeah, based on the applied electric field in general, epsilon of that medium will change. If that changes, this guy also will change. And therefore, there is no linearity holds between these two quantities. So now we are assuming nothing happens like that. For any electric field, epsilon will be just like that. It doesn't change. So therefore, D also doesn't change. So linearity holds well. All right. So we keep this assumption first of all, and that's what the linear word. This linear word will justify this assumption. And now homogeneous. Anyone in the class? What is homogeneous medium? Hmm? What is homogeneous medium?
Sir, epsilon must be constant throughout the medium.
Excellent, very good. Thank you. You just gave a gunshot answer. That's great here. So without exaggerating something, that means, see, okay, if you practice for say GRE course, you will come across many words. There is a very interesting word, belabor, right? What this means? Belabor means what? Whatever is required, just give the answer. Just don't tell unnecessary points. Okay, that's the meaning of this belabor. If someone says you don't belabor your answer, means the meaning is right now. Who gave this answer? I think
Hemant, sir.
who gave this answer now?
Roll number 10, sir.
Roll number 10.
Yes, sir.
Okay. So roll number 10, he did not belabor his answer. So he just gave straightforward answer. And these answers are really important. So people who really give straightforward answers, they definitely get through interviews. This is fact. So it's not that, because thing is that if you have clarity, then only you can give simple answers. That's it. It's great. Very good. So as your friend said, the answer is, I have a medium. Yeah. So in this case, epsilon, this guy is spatial. I mean, I can write like this. This guy is position independent, and also time independent. That means generally in free space, epsilon, if I take in Cartesian system, this is a function of space as well as time. So now epsilon is just independent of space as well as time. That means wherever I go within this medium, I take subregion, region 1, subregion 2, subregion 3, subregion 4. Wherever I go, I find same epsilon. Yes or not? And this is what homogeneous medium means in simple language. Wherever I go, I just find same epsilon. That doesn't matter. So therefore, it will not really disturb my linearity as well as homogeneity property. And what about isotropic medium? Anyone?
Sir, constant temperature.
No, we okay.
Sir,
Isotrope. Uh,
like the properties will be same when we measure in different directions.
Excellent. Very good. This is again a straightforward answer. For example, you have a medium again. Okay, this medium is said to be isotropic. For example, your E wave is traveling in this direction, and in the medium it is traveling in this direction. So when the E wave is traveling in this direction, the properties of the medium, yeah, the properties of the medium will be, yeah, in some level of, okay, it is at some level now, for example. Okay, now an electromagnetic wave, for example, EM wave is traveling something like this in this medium. So this doesn't change. The properties of the medium will remain same however you travel in the medium. However means in what or direction you travel doesn't matter. Now second time I go this way, I come like this, I go this way, I mean I go this way. However you go in this medium doesn't matter, medium remains same. I mean the medium properties will never change. Okay, so this kind of beautiful medium is a hypothetical isotropic medium. Okay, this is really hard, this is highly impossible in general, but still we can approximate this, not a problem. Now there is something called as anisotropic medium. Anisotropic medium. This is pretty interesting one that you will come to know later, but I don't think you have this in this course. But for example, you have a medium. Okay, now you see when EM wave is traveling like this in this direction in the medium, now according to the direction of travel, the properties of the medium will change. Yeah, for example, the wave is going this way. Now again it will exhibit different properties. The medium properties will automatically change by itself when wave is going this way. When wave is, suppose for example, going this way, again the properties will change. The properties of whom? This medium. This guy is going this way. So this is the problem. I mean, this is the case with anisotropic medium, but this isn't the case with isotropic medium. So however you go, doesn't matter. The medium properties remains the same, and so therefore we are taking all these flexibilities. Okay, isotropic medium, homogeneous case, and also linear case. So a single medium satisfying all these three conditions: linearity, homogeneous, and what isotropic, like you say linear time invariant, you remember that. Now you remember linear homogeneous isotropic chai medium. Okay, so now what I do is next time I think I have to use Microsoft whiteboard so that I need not waste my time for all these things.
Then mu becomes again m will come.
So now in general case, in general medium, this mu and epsilon, they are just position and time dependent. So I take minus j omega mu h, and I take again curl of h is equal to positive j omega epsilon capital E. Okay, now I know this E, curl of E is equal to this, and from this let me find out h. Let me find out h. H is equal to, I have negative 1 over j omega. I have mu inverse, and I have curl of E. Okay, now what I do, I put this h in this. From this I found h. Let me put this h in this. Now from this what I found is, what I can find is this curl of minus 1 by j omega mu inverse curl of E is equal to j omega epsilon E. See, I'm making my things complex in going all the way. Okay. Now, anyways, this last equation is simplified. See, because is 1 by j omega varying in space? Is 1 by j omega is a space variable?
No, sir.
Yes or not?
No, sir.
Is 1 by j omega is a space variable?
No, sir.
No? So it's a constant, so I can happily bring it to right hand side. So therefore what do I do? So curl of, I take this guy, curl of mu inverse Again, curl of E is equal to J multiplied by J is minus 1. So minus multiplied by minus is positive. I mean, this minus minus will be cancelled out, sorry. So therefore, you get omega square epsilon E. Now you tell me, can I bring this mu inverse towards right side?
No, sir.
Yes, sir.
Yes,
No
sir.
or yes? I can't bring. This is a general medium. So this is inhomogeneous. Okay, if I say like this, if it is inhomogeneous media, now can you bring this?
No, sir.
No,
Now you
sir.
cannot take.
No, sir.
This is
No.
impossible because this guy is space dependent and also time dependent. And this curl, nabla, when I say, for example, if I take Cartesian system, nabla is what now? Dou by dou x ax plus dou by dou y ay plus dou by dou z az. All right. So nabla, this nabla is a spatial derivative, and this guy is again spatially dependent. So this guy is different along x-axis, different in y, different in z. So this is of course spatial dependent. Now you have spatial curl in the left hand side, and this guy is a part of it. So therefore I can't really make him appear on the right hand side. It is impossible. So therefore in inhomogeneous medium, mathematics is quite not at all trivial. I mean, it's not at all simple, I mean to say. So therefore this equation is not very useful for performing derivations. Okay, so this is what you have to understand. See, because when you see the equations, list of the equations, you should be able to identify which is helpful for the further derivations or which isn't. So that's so that judgment capability one must have. So now I can clearly say this will really, this will create a havoc. We can't really move anything with this equation. So therefore, but you know what, this uh, this equation is good. This is used in
So
numerical
much.
computations. This must be there. That means this equation is good when you try to evaluate things. When you try to evaluate things where,
Homogeneous media, sir.
yeah, no, yeah. What I want to say is this, and this is good. This is really good when you are programming this, or when you use a computer. Just use, I just drew a computer like a TV, think it's a computer. So if you want to, numerical computation means you're using computer to analyze something, okay? So in this case, it is a good equation, but if you want to do in hand, it is not really a favorable equation. So therefore what we do now, we will restrict our medium to be a homogeneous medium. So when you have a linear homogeneous, just 2 minutes, if I take, I must copy this. So when I just take there, I don't save it. Okay, I don't save it. Okay. Okay, now you just tell me, now I have a beautiful medium. Now my medium is linear, my medium is homogeneous, my medium is also isotropic. Okay, now you tell me, can I bring this mu towards right hand side?
Yes, sir.
Yes, sir.
Yes, sir.
I
Yes,
can
sir.
happily bring this guy because now in homogeneous case, both mu and epsilon are beautiful constants,
Mm.
simple constants. So I can bring this guy towards right hand side. So now let me take this down. So I have curl of E is equal to, this guy is coming towards right hand side. and you have omega square mu epsilon e. Okay, so you have this. Now this is what in this linear homogeneous isotropic medium. Now again, what else we can decide from this? So let me go for a vector identity. Let me go for a vector identity, and that says curl of any vector you take is what? Gradient of divergence of that vector minus Laplacian of the vector. So Laplacian operator is possible both on vector as well as scalar. So generally, the gradient of divergence of A minus Laplacian A. How do you remember this? Just remember this gradient. Okay. Remember, start unlock this identity. You start with this the word gradient. So in this case, first there is gradient, and then say there is divergence. Okay. So then write like this here: gradient of divergence. Okay, gradient of divergence of that vector minus Laplacian of the vector. Always remember identities in terms of words. Okay, then this becomes simple. If you remember them, it's gone. Okay, so I just apply it over here. So if I apply this over here, now this becomes gradient of divergence of E, all right, minus Laplacian of E is equal to omega square mu epsilon E. All right. Now I just put these two guys on one side. So let me put these two guys. Say you have del square E plus omega square mu epsilon E is equal to, I have on the right hand side gradient of divergence of E. Okay. Now, of course, you have linear homogeneous isotropic medium. I take the same medium here. Now, you tell me my medium is source free. Okay. When my medium, there is no further source, there is no further charge, for example, existing in the medium, there is no charge, nothing. That means I could say rho v is equal to 0. When this is the case, what is divergence of D?
0, sir.
0, sir. 0, sir.
Yeah, divergence of D is equal to 0. And this guy is again homogeneous medium. When this is homogeneous medium, and of course you're in free space, so epsilon r is close to 1 and D is epsilon naught E, this becomes 0. All right. So this guy epsilon naught or epsilon whatever in homogeneous medium is perfectly constant. I bring this guy out, you have divergence of E, this guy should become 0. So can I make this happily divergence of E 0 at the end? Yes, sir, not?
Yes, sir.
Yeah,
Sir.
so with that clarity, you plug in that stuff here. So divergence of E equal to 0. So gradient of 0 has no meaning physically, mathematically, physically, they don't have any existence. So therefore, so I'm using more colors. Dasara bullard madri colors use chestnano. Del square plus omega square mu epsilon E equal to 0. So just now you have finally the final touch is this. So del square E, I replace this omega square mu epsilon as k square, or I can also replace this omega square mu epsilon as negative gamma square. And it will be evident why are we taking these two forms. Okay, either you use the first form or the second, you will land at the same set of equations, but it's only a convenient point of view. I just take k square in the initial run. So I have omega square mu epsilon as k square and this E as E. So this guy is this. So now we arrived at this beautiful form del square E plus k square E equal to 0. And if you find the solution of this particular equation, differential equation, Now what you get? You get two traveling waves. One is forward traveling wave and the other is backward traveling wave. We have to sum up these two traveling waves, and that must be the solution for this. And in doing so, in the exponents, you will have to find imaginary terms. So you get in the solution, you have e power something. Okay, e power something. That something will start with plus or minus j. If I take plus k square here, if I plug in omega square mu epsilon equal to negative gamma square, then I get what now? Del square E minus gamma square E equal to 0. In that case, in the exponent, I don't see any j term deliberately. Yeah, there will be no j term, but I can see this gamma in this exponent position. But whatever, you have to accept that this gamma is first of all a complex quantity. So this gamma is again alpha plus j. That means this j is hidden within this gamma. So anyways, in the exponent, you have to have this imaginary stuff. So if you want to see that directly, just take k square. If you don't want to see it directly, just take gamma square, and things will be evident in our subsequent lectures, like gamma is a complex quantity, and this decides the propagation constant. And again, you have this alpha and the beta attenuation constant and phase constants, and we have to segregate again. People keep saying that beta and k, they are same. They are not same at all. Yeah, beta, somebody say beta, you can replace beta by k. You can replace beta by k only in free space. Yeah, only in free space, or only for TM case, transverse electromagnetic case. When the wave is traveling by satisfying this particular mode, in that case only I can use beta and k, both are same. In any other, for example, if you're using TE and TM modes individually, then beta and k, they are not same. So anyways, we are dealing with a wave propagation in free space or vacuum, and our wave will exhibit this nature, transverse electromagnetic nature. So therefore, happily we can treat beta as k or vice versa. Okay, so let's try to understand these parameters in more detail in our subsequent lectures again. So you have certain parameters to keep with you. So those parameters you have to put at right places to solve further equations. So once you're able to solve these equations, the remaining part is directly problem solving. It's very simple. So I think we have 2 more classes for derivations, and then we can devote the rest of the classes for problem solving. Okay, as I already told you in beforehand, I think I just told to CRs Manoj and Niharika, you just please assign some other class, I mean some extra classes. Just tell me when can I take extra classes, so I don't disturb you on Sundays, on Saturdays as well. So other than these 2 days, just tell me. Extra classes I require, as I told you, 10. Okay. Okay, then we will end up here. So CRs, please do consider this, and
Yes, sir.
please see to that we get extra 10 classes. Okay.
Okay,
Okay,
sir.
sir.
Okay, fine, thank you. Any questions, please? No questions, then fine. Okay, thank you.